Welcome to section 7.3. We are going to start taking the tools that we learned in section 7.2 regarding partial derivatives and now apply them to the optimization of functions of two variables. So first we're going to define what it means for a point to have a max or min value for these functions. And then we'll talk about kind of the implications of that and how we can determine those. So we say that the point AB produces a relative maximum of the function f of xy if for every point xy near AB, f of AB, that's the output at AB, is greater than or equal to f of xy. And this is again for xy values near AB. So a relative maximum is produced when the output, the height at AB, is greater than or equal to everything else around it. Similarly, the point AB produces a relative minimum of the function f of xy if for every point xy near AB, f of AB is less than or equal to f of xy. So if the output at AB is smaller than everything else around it, then that's a relative minimum. So conceptually, these ideas are the same as max and min values for functions of a single variable. Where this changes is how we determine where these points might be. So we can say if f has a relative max or min at AB and fx and fy, the partial derivatives, exist there, then fx of AB equals 0 and fy of AB equals 0. So back in single variable, we had a relative max or min, and the derivative existed there. Then that told us that f prime of x was equal to 0. But now we don't just have f prime anymore. We have two derivatives. We have fx and fy, the two partials. So both of those are equal to 0. Now, this is saying if we already know that there's a max or a min there, then this is true. We want to go the other way. So we are going to say a point AB is called a critical point of f if fx at AB is 0 and fy at AB is 0, or if one of these partial derivatives does not exist. And now we want to use critical points to determine where maxima and minima might be. So once we determine where the critical points are, by setting these partial derivatives equal to 0, solving for any points that occur out of that, we need to be able to test these values, these critical points, to see if they do produce a maximum or minimum, because we don't have that guarantee. We still need to check them. So this brings us to the second derivative test. So back for single variable, we had a couple different tests that you could use. This one, there's only one. So second derivative test says, suppose the second partial derivatives of f are continuous near the point AB, and suppose fx and fy are both 0 at AB. Let d equal fxx at AB times fyy at AB minus fxy at AB squared. So we have fxx times fyy minus fxy squared. And we need to plug in the point AB into this formula. Once we find all those second partial derivatives, the result that we get for D is going to give us information. So for parts A and B, we have the cases where D is positive. So if we get out a value of D that is a positive number, then that tells us that there will be either a max or a min. Okay, so this right here, if D is greater than 0, tells us there will be either a max or a min. But we don't necessarily know which one. So we have a little bit of extra checking to do. So we're going to check fxx. If fxx is also positive, so D is positive and fxx at the critical point is also positive, then this point is a relative minimum. If fxx is negative, however, then our point is a relative maximum. Okay, so if we run this second derivative test, this is sometimes called the D test. If we run the D test and we get that D is positive, that means there will be either a max or a min there. Which one is it? Well, that depends on fxx. So we check fxx to get whether it's positive or negative. If D is positive and fxx is positive, that's a min. If D is positive but fxx is negative, that's a max. Okay. Now, if D is negative, if D is a negative value, then f of AB is what we call a saddle point. The saddle point is kind of like the neither case. So neither a max nor min. The reason we call this type of point a saddle point is because if you were to look at the graph of it, it would look something like this. Yeah, something kind of like that. So it looks like a saddle, right? If you picture, like, if you're riding a horse, right? The horse goes in this way and then your legs are on either side of the saddle like that. So the saddle point is neither a max nor a min, because if you look at it from one direction, it looks like it's a minimum. But if you look at it from the other direction, it looks like it's a maximum. So it doesn't satisfy either of the qualifications to be a max or a min. And then we have our last case. This is the case when D equals 0. If D equals 0, then this test is inconclusive. So this is the unfortunate outcome out of all of these, because then that means that there's not much we can do with it in using this technique. This is, for our purposes in here, relatively uncommon. Obviously, I don't want to give you guys lots of problems that you can't go through the solutions to and like actually work on and practice with. But this can happen, so we just need to be prepared for that. That is a possibility. And if that is the case, then we would have to use other means, either algebraic, geometric, like visually, graphically, or using other techniques that we haven't learned here. All right, let's try an example. Find the local maxima, minima, and saddle points. That should say relative. This is just another word for relative. I think sometimes the texts use one word and sometimes my notes use another. But find the local or relative maxima, minima, and saddle points for this function f of xy. So in order to do this, we need critical points first. In order to get critical points, we need to take the partial derivatives and set them equal to 0 and solve. So we're going to take fx and fy and we're going to set these equal to 0. And now we solve for x and y however we can. So this one, I'm going to add the 4y over and divide by 4. So we end up with y is x cubed. And I'm going to use this in the second equation. So we get 4x cubed minus 4x equals 0. So that's divide by 4, that's x to the 9th minus x equals 0. So if we factor out an x, and then x to the 8th minus 1, so we're going to get x equals 0, and then this one is going to give us a negative 1 and a positive 1. Okay, just like if x squared minus 1 was equal to 0. We need to find the y values that correspond with these. So just sub back into here. So y will be 0 cubed. Y will be negative 1 cubed is negative 1. 1 cubed is 1. So it turns out the y values in this case will all match their corresponding x values. So our critical points are, I'll go in numerical order, negative 1, 0, 0, and 1, 1. So this is our first kind of milestone in the problem. Next, we need to test these critical points. So we need to get the formula for d, for that d test, that second derivative test. We need to take the second partial derivatives. So we're going to get fxx, that's going to be 12x squared. Fyy is 12y squared. And fxy is just negative 4. And then d of xy is fxx times fyy minus fxy squared. Be very careful with negatives in these expressions. This negative is not applied to this 2. So no matter what there is in here, this will always be a negative. And let's see, this gives us, that's 144 x squared y squared minus 16. That's our formula for D. And we're going to use that to test all of the critical points. So D of -1, -1, 0, 0, and 1, 1. So we get 144 minus 16, that's 128. 0, 0, we get negative 16. 1, 1, we get 128. Now, it doesn't even really matter what the number is itself. What really matters is the positivity or negativity. So we have a positive, a negative, a positive. The negative case, we already know, means that there's a saddle point there, right? So it's not a max and it's not a min. These two, the positive zeros, the values that are positive greater than 0, these are going to be either a max or a min. We don't know which one until we test. So we're also going to take fxx of -1, -1. That's going to be 12 times 1, that's 12. That's also positive. And fxx of 1, 1 is also 12. Those work out the same. All right, so for our conclusions here, so we'll take, relative max, relative min, and saddle points. So when D is positive and fxx is positive, that's a min. So that means the first one and the last one are both minima, and the D being negative is a saddle point. It's good to, when finding the points themselves, to plug back in to the original function to get the z value or the f of xy value that goes with them. So relative max, we have none. Relative min, -1, -1. If you plug that back in here, you get 1, 2, minus 4 is -2, plus 1 is -1. So we get -1, -1, -1, and 1, 1, -1. And the saddle point is 0, 0, 1. And those are our extreme values. Those are our optimized values for this function. So let's try another example. Look at something similar. Locate the relative extrema, if any exist, of this function f of xy. So we're going to take fx and fy. So fx, bring down the 3, but it cancels. So we get 2x squared minus 50. And then fy gives us 4y squared minus 16y. We're going to set these equal to 0. Let's see, we get x squared is 25, so x equals plus or minus 5. This one, we get 4y, and then y minus 4. So we get y is 0, and y is 4. So we have 2 x values, 2 y values. So our critical points, we're going to take, so we'll start with the negative 5s. Negative 5, 0, negative 5, 4, and then 5, 0, and 5, 4. Now, in order to test them, we need to take the second derivatives, the second partial derivatives. So we have fxx, that's going to be 4x. Fyy is 8y. And fxy is 0. So we get 32xy minus 0 squared. So don't even need to include minus 0. And now we test all of these critical points. So get these two. Oh, did I mess something up? I did mess something up, didn't I? Have you been shouting at me through your screen? Oh, wait, this isn't working. Where did we go? So fyy, that's 8y minus 16. There we go. Minus 16 in there. So when we multiply these two, we get 32xy minus 64x. All right. So now we can keep going with this. Oops. All right. Well, the case where y is 0 turns the first term into a 0. So that ends up giving us negative 64 times negative 5, which is positive 320. Negative 5 and 4 gives us actually negative 320. 5, 0 gives us negative 320. And 5, 4 gives us positive 320. The negatives are done. The positives we need to investigate just a little bit further. So we get negative 20 and oops, I messed that one up too, didn't I? Are you yelling at me again? That should be positive 5, positive 4. The number was right. This number was right. So we get 5, 4, which is going to be positive 20. So if we're looking just at kind of quick labels here, D is positive, fxx is negative. That's going to be a max. D is positive, fxx is also positive. That's a min. And the negative values for D mean that there's a saddle point. Now, for this one in particular, finding the output values of the function is a little nasty. The fractions kind of make that a little bit tougher, but it's still doable, and you have calculators. So if we look here, we have relative min, relative max, saddle point. So the min is going to be at 5.4. The output for that is negative 625/3. The relative max, we have negative 50. And the output for that one is 503/3. And the saddle points are the other two. So negative 5.4, output of 125. And 50, output of negative 497/3. So we see through these kind of repeat examples that we are having, even though the functions change, the specific numbers change, the overall process remains the same. This idea of taking partial derivatives to find critical points, finding the D value and running that second derivative test, and then drawing a conclusion. So let's take a look at the next page. We're going to have an example here that is more of a modeling problem, more application-based, but still using the same techniques. So a manufacturer markets a product in two states, A and B, and because of the different economies of the states, must price the product differently in each. The manufacturer wishes to sell X units of the product in state A and Y units of the product in state B. To do so, the manufacturer must set the price in state A at 86 minus X over $18 and in state B at 122 minus Y over $28. The cost of producing all X plus Y items is $45,000 plus 4 times the quantity X plus Y dollars. How many items should be produced for states A and B respectively to maximize the manufacturer's profit, and what is that maximum profit? Okay. So we got a lot going on in here. So we have X units in state A, Y units in state B. The price in state A is given here. The price in state B is given here. And the cost of producing all X plus Y items is given here. And it's asking how many items should they produce to maximize the manufacturer's profit. And then what is that profit? So we're trying to maximize profit, which means we need a profit function in order to do this, but that means we need cost and revenue functions. So profit is equal to revenue minus cost. Revenue is price times quantity sold. We know the price for state A is going to be 86 minus X over 18 times the quantity sold is X, plus price for state B, 122 minus Y over 28 times quantity sold is Y, minus cost, which they gave us the formula for cost. So minus 45,000 plus 4 times X plus Y. so if we combine like terms and simplify as much as possible, I'll tell you what we get out of this. We get 82x plus 118y minus x squared over 18 minus y squared over 28 minus 45,000. So because we're dealing with an application here, there was that little bit of extra work we needed to do just to get to the formula. So this is the profit function that we're going to be working with. So we need to find critical points and then test them. So let's go ahead and we'll take px. So that's 82 minus let's see if this is bring down the 2, yeah, just x over 9. And then that's 0, 0, and 0 with respect to x. Py 118 minus y over 14. So similar. We're going to set both of these equal to 0. Add this over, multiply by 9, we get 738 for x. Same thing, multiply the y, we get 1652 for y. So practical numbers, not always the easiest numbers, but the fact that they're whole numbers I think is already still a good thing. So we have our critical point. Now we need our second partial derivatives. So pxx is negative 1/9. Pyy is negative 1/14. And pxy is 0. So an interesting thing happens in this one. When we take d, we take negative 1/9 times negative 1/14. That's positive 1 over 126 minus 0 squared. This value is not dependent on x and y, right? It's technically a function of x and y, but there's no x's and y's in it. So it doesn't really matter what the critical point is. This number will always be the same. So d of 738 1652 is still 1 over 126, which is a positive number, which means there will be a max or a min. And then if we check pxx at 738 1652, which again, it's still just going to be negative 1/9. That tells us we have a maximum there. So this does produce a maximum. And then the question is, how much profit are they getting at this maximum? So we would take P of 738, 1652, which for the sake of your sanity, I will just tell you is 82,726. So the question was, how many items should be produced for states A and B to maximize their profit, and what is the maximum profit? Now we see now they should produce 738 items for state A and 1,652 items for state B. This would give them a maximum profit of $82,726. So we apply the same techniques that we saw in the previous examples, and then we just make sure that we answer the question properly, we answer what it asked for, and we answer within the context of the model. But that brings us to the end of section 7.3. So when we come back in the next one, we will be finishing off the chapter with section 7.4. So I will talk with you all in the next one.